Yep, so in the last video, I left you with the change of base formula and then talking about how we're going to find derivatives of log functions with bases other than e. Just a real quick look at something first before we get to the formulas, and don't write this down, just kind of watch what I'm doing here. If I'm looking at finding the derivative of log x base a, or log base a x, okay, I can also write it as log of, it's equal to log of x divided by log of a, which now we know from this work up here that this is also equal to the natural log of x divided by the natural log of a. And I want you to just think about this for just a second as we move into the formulas and why the formulas look the way they do with these log derivatives. Anyway, this is just taking log of x base a, rewriting it, change of base formula. It doesn't matter what log we're using or what base. This is equal. But I also want you to consider that this is just a constant. This is just a constant right here. And in our work with constants in the denominator, we can actually pull that out as a constant multiplier. That's going to be some number once I've established what a is. So this is really 1 over natural log of x times the natural log, 1 over natural log of a times, the natural log of x. So we can just look at this as a constant multiplier, if you will. So just want you to kind of think about what we have here. What we're going to be doing is finding a derivative here. Well, if this whole equation can be rewritten like this, just think about this for a minute. If you were asked to find the derivative of this expression, which is equal to this expression, well, if I'm going to find this derivative, it's actually just the derivative we've already found of natural log of x. This is the constant multiplier, so it's 1 over natural log of a times 1 over the derivative of natural log of x is just 1 over x. So it's just weird how, I guess, an log derivative transforms and morphs into an ln derivative answer. And that's just because of the change of base and the equivalent thing that we can do here. All right, so let's take a look at this. Actually, you probably have more room than I do, so I'll try and write small, but we're looking at two derivatives here, formulas. Okay, so here's one formula right here. So if I have y equals log x base a, if I bring in the derivative operator, just another way to write what I've done previous here. Okay, then this derivative would look like this, dy dx. You can find the derivative. It's equal to, okay, now over here, the formula is constant multiplier, 1 over the natural log of whatever the base is, times 1 over x. And just what we said over here. If you think about the derivative here, that would just be 1 over x. Okay, the other function that we might be dealing with is going to be a composite log function. So I'm not going to use the y equals notation, just different notation I want you to get used to. Okay, what's different here is that instead of this just being a simple x, it might be x squared. It might be 3x squared minus 2. I don't know what u is going to be. It's just more complicated, more complex. So it's the chain rule. So I'm going to, let's see, I guess work down here maybe. Save myself some room. So the derivative, I'm going to put equals. Okay. All right, looking at this, if I see a log function, immediately I'm thinking, well, I have a constant multiplier of 1 over natural log of a. I'm building a fraction. Times, now it's going to be 1 over u, whatever u is, the inside function, times the derivative of u with respect to x. So that would look like du over dx. And we could write that as u prime. So these are the formulas. Unfortunately, we're going to have to memorize. There are no formula cards on the AP test, so that is the bad news. But hopefully through use and practice, we'll commit many of these to memory, and that's never been a problem for the students. All right, I'm given this random logarithmic function with the base 2, and I'm asked to find the derivative, because perhaps my objective is to plug in some coordinates to get a slope, or maybe my objective is to get the equation of a tangent line, which would require all this work from me as well. So thinking about what the formula is, y prime 1 over the natural log of 2, the base, times, okay, go ahead and establish this to be your u, 1 over 5x times the derivative with respect to x of the 5x. Which I know many of you are going, well, that's 5, and that's absolutely fine. Let's build a single fraction here. Okay, I'm going to put 5 on top. Natural log of 2. It might look better if we put it in parentheses. Times 5x. Yes, we can simplify. We can divide out the 5, and that would be a very, good thing to do. That's fine. Okay, so my y prime, 1 over, I'm going to go ahead and make this x ln 2. All right, we have a composite log function. We're interested in finding the derivative. All right, it's a log function. So notice there's no base on it. We know the understood base is 10. When I go to find the derivative, I take care of that constant multiplier first. I say it's 1 over the natural log of, well, that's 10. That's the understood base. Times, okay, go ahead and establish that as u, 1 over 3x plus 1 times the derivative of u, the derivative of the inside function, which is 3. And I'm going to go ahead and put that right here, times 3. Instead of writing the notation, that's easy enough. Okay? All right, cleaning it up, it looks like I'm going to have a 3 on top. I'm not going to be able to cancel with this 3 down here because I can't go into that quantity there. Natural log of 10, 3x plus 1. Okay, so if I needed to find a slope, I would need to know the x value, the point on the graph, and I could plug that in for the x given. Plug that in for the x value here. Oh my goodness. Okay. Okay, stop. Right, so I don't know where all that went to, but I'm hoping that you have it all there. My last comment was that you could not divide these threes out right here. So you're going to have 3 over, it looks like this may have been a 3x plus 1. Please don't disappear. Okay, and then that's it. That's your derivative. So not too bad. Hopefully that helps with the lesson next at hand.